Hi everyone, I am Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung-0309 University. This is my name in Chinese, Chung-0309. Welcome to the course Seismic Evaluation and Retrofit of Structures. This is the lecture on Preliminary Evaluation 1. Preliminary evaluation is one of the stages to screen out those buildings that are not qualified in seismic performance. From comprehensive survey, we know that what year a building was constructed. If the building was constructed before 1999, it may be moved to this stage, preliminary evaluation. And today we will focus on the seismic capacity by preliminary evaluation. Here are some terminology. Seismic capacity is the earthquake level that a building can resist. In Chinese, 耐震容量. Seismic demand is the earthquake level that a building may face in its surface life. In Chinese, 耐震需求. Ultimate base shear strength is the maximum base shear strength of a building. In Chinese, 极限基底剪力强度. Vertical structural members, in Chinese, 垂直构件, including reinforced concrete column, in Chinese, 钢筋混凝土柱, reinforced concrete wall, in Chinese, 钢筋混凝土墙. Four-side bounded brick wall is a brick wall bounded in four sides. In Chinese, 四面围疏砖墙. Three-side bounded brick wall is a brick wall bounded at three sides and open at the fourth side. In Chinese, 三面围疏砖墙. Lateral force per unit cross-sectional area. In Chinese, 单位断面积强度. Once we know the lateral force strength per unit cross-sectional area and the cross-sectional area of the vertical member, we can calculate the lateral force strength of the member. For preliminary evaluation method, it should be simple. That means that it can be finished in a little bit amount of time. It's fast, it takes a little amount of time, and it's economic, it's cheap, it's effective, and discrimination. That means that we can differentiate which building is qualified, which building is not qualified. And the method must be objective. That means that the preliminary evaluation of building conducted by two different engineers, but the results should be very similar, so that the method must be objective. For school buildings, preliminary evaluation is conducted by professional engineers according to the result of comprehensive survey. That means only buildings constructed before 1999 would be moved to this stage, preliminary evaluation. And it takes half a day for a building, and it costs $6,000 for a building. And the result from preliminary evaluation is seismic index. If seismic index is less than 80, and it will be moved to the next stage, detailed evaluation. All the results from preliminary evaluation have to be submitted through internet to NTUST, our center. From preliminary evaluation, seismic capacity is determined by the cross-sectional area of the vertical members in the first floor, and the seismic demand is calculated by the location where the building is located, usage, is it used by the students, and number of stories. And in this case, number of stories equal to 3, 1, 2, 3 is a 3-story building, and the total floor area above the ground including the second floor, the third floor, and the roof. And the result is adjusted by the condition of the building, including settlement, is there any settlement, any crack, any leakage. And the result is seismic index, is the capacity to demand ratio, and adjusted by the conditions of the building. From seismic design codes of building, equation 2-3, we have the design seismic force, V equal to I divided by 1.4 alpha y, SAD divided by FU, modification times W. V is the design seismic force, is the minimum base shear of the building, is the minimum base shear strength of the building. I is the importance factor, and SAD is the spectral acceleration, design spectral acceleration. That's the acceleration response under design earthquake. And W is the total weight of the building. That's the dead load of the building. Alpha Y is the first yield seismic force amplification factor. Because the seismic design force has been reduced by 1.4 by alpha Y by FU, so the V here is the elastic seismic force. And after multiplying by alpha Y, it becomes a yielding force. And FU is the seismic force reduction factor for structural system due to ductility. And SAD divided by FU modification, the ratio is modified due to soil structure interaction for the high damping ratio. Since the design seismic force is the minimum requirement, therefore the actual base shear strength of the building must be larger than or equal to I divided by 1.4 alpha y times SAD divided by FU modification times W. If we move 1.4 alpha y to the left-hand side of the inequality, then we have 1.4 alpha y times V larger than or equal to I times SAD divided by FU modification times W. And if we further move this term to the left-hand side of the equation, so that we have the fraction here, 1.4 alpha y V divided by I times SAD FU modification times W must be larger than or equal to 1. If a building is well designed, or if the building have enough seismic capacity, the capacity to demand ratio must be larger than or equal to 1. So that the numerator here, the numerator here, we can call it seismic capacity equal to 1.4 alpha y times V. The denominator here, we can call it seismic demand, I times SAD divided by FU modification W. And in this lecture, we will focus on seismic capacity of a building. And here is the force displacement relationship of a structure, of a building under earthquake. And this figure is taken from the seismic design codes of building, figure C2-1. When the displacement of building is small, it's linear. There's a linear relationship between the force and displacement. When the displacement becomes larger and larger, the stiffness of the building becomes smaller and smaller. PD is the design seismic force. Because it has been reduced by 1.4 alpha y, we reduced by FU, so that the design seismic force is an elastic force. After amplifying by alpha y, it becomes a yielding seismic force, and is further multiplied by 1.4, and then it becomes ultimate seismic force. And 1.4 here is countered by the redundance of the structure and the strength hardening of the material. And delta here is the structural displacement. Therefore, 1.4 alpha y times V is the ultimate seismic force of the building. And here's a typical building. And from the front elevation view, there's first floor, second floor, and third floor. And from the plan view, 1 classroom, 2, 3, 4. There are totally 4 classrooms. And 1 staircase here, 1 staircase here, and 2 staircases. And here's the restroom. Dead loads of the building accumulate from the roof to the first floor. Therefore, the first floor demand is the highest. From the elevation view, the dead load of the building accumulated from the roof to the third floor to the second floor. Therefore, the dead load demand on the first floor is the highest, or the vertical load due to dead load is the highest in the first floor. Similarly for live loads accumulate from the roof to the first floor, so that the demand of live load is the highest in the first floor. The live load from the roof accumulate to the third floor and then to the second floor, so that the actual load due to live load on the first floor is the highest one. Similarly for seismic forces accumulate from the roof to the first floor, so that the story seismic shear is the highest in the first floor, so that the first floor demand is the highest. However, the story shear strength of the first story may not be higher than the story above. The demand is highest, but the strength may not be the highest, so the first floor dominates the seismic performance. Another characteristic of this existing building is that the beam is usually stronger than the column, so that we can come up with the result that, with the conclusion that vertical structural members, including columns and walls, in the first floor dominate the seismic performance of the building. Along the corridors, there's opening for windows, for doors, so that passage and ventilation and daylight is available. Therefore, the amount of walls along the corridor is less. And transfer to the corridor, there are partition walls 1, 2, 3, 4, 5, 6, and 7, so that the amount of walls may be more. Therefore, the conclusion is that along the corridor is the weak axis of the building. And perpendicular to the wall, to the corridor, if we consider the cross-sectional area of the column, the dimension of the column, the dimension transferred to the corridor is higher than the dimension perpendicular along the corridor, so that perpendicular to the corridor is the strong axis of the columns, and along the corridor is the weak axis of the column. So that the conclusion is that first floor vertical members, columns and walls along the corridor dominates the seismic performance. And as we know, 1.4 alpha y is the ultimate seismic force, and it can be considered as the ultimate base shear strength, VBS. Therefore, VBS equal to 1.4 alpha y times V. And how do we calculate VBS? And VBS is calculated by the sum of lateral strength of vertical members. We just superimpose all the lateral strengths of the vertical members. Since the ultimate lateral strength may not be developed at the same time for all vertical members, so that the summation is reduced by a reduction factor for the ultimate lateral strength beta. After reduction, then we can have VBS equal to beta times VVM, and VVM is the sum of lateral strengths of vertical members. VM here stands for vertical members. Vertical members including reinforced concrete column, reinforced concrete wall, 4-side bounded brick walls, and 3-side bounded brick wall. And 4-side bounded means that it's bounded by beams at the top and bottom. It's also bounded by a column at the left and the right. And 3-side bounded brick wall is bounded by beams at the top and the bottom, and is bounded at one side, the left side or the right hand side, by a column, and it's called 3-side bounded brick wall. And 2-side bounded brick wall is a brick wall bounded by the beams at the top and the bottom, and no boundary at the left hand side and the right hand side. Since the 2-side bounded brick wall, the strength of 2-side bounded brick wall is not that high, so that its strength is neglected. And only in-plane strength of the wall is taken into consideration. Therefore, the out-of-plane strength of the walls, including concrete wall or brick wall, is neglected. VBM is the sum of lateral strengths of vertical members by this equation. VBM equal to tau C times AC plus tau RCW times ARCW plus tau BW4 times ABW4 plus tau BW3 times ABW3. Tau here is the lateral strength of the vertical member per unit cross-sectional area. And A is the cross-sectional area of that vertical members. And subscript C stands for first floor reinforced concrete column. RCW, first floor reinforced concrete wall. BW4, first floor 4-side bounded brick wall. BW3 is first floor 3-side bounded brick wall. And this is the plan view of a classroom. This is the front side of the classroom. This is the rear side of the classroom. And the column at the front side of the classroom and the rear side of the classroom are considered as column of classroom. And to the exterior of the corridor, there may be some columns here. They are called columns of corridor. And inside the partition wall, a column may be embedded, and it is called column of partition wall. From statistics, tau C for column of classroom equal to 1.8 NF plus 4. NF is the number of stories, and for column of corridor, tau C equal to 1.08 NF plus 2.4. And for the column of partition, tau C equal to 2.6 kgf per cm square. And the unit for tau C is kgf per cm square. Usually, the column of classroom has the highest dimension. Since the columns of classroom have a largest cross-section, so that the ratio of the core concrete area to the cross-sectional area is highest, so that the unit lateral strength, the lateral strength per unit cross-sectional area is the highest for the column of classroom. And the next one is column of corridor, and the least one is column of partition walls. In general, if we have higher stories, that's the larger number of stories, then we will put more reinforcement to the first floor column, so that tau C, the lateral strength per unit cross-sectional area, increases with the number of stories for column of classroom and also for column of corridor. However, for the column of partition wall, the reinforcement will keep unchanged for different number of stories, so that the unit lateral strength remains the same no matter what the number of story is. And for reinforced concrete wall, the unit lateral strength tau RCW equal to 12 kgf per cm square. For four-side bounded brick wall, the lateral strength per unit floor area, per unit cross-sectional area, tau BW3 equal to 3 kgf cm square. And for three-side bounded brick wall, tau BW3 equal to 2 kgf per cm square, so that the unit lateral strength of the reinforced concrete wall is the highest. The next one is four-side bounded brick wall, and the least one is three-side bounded brick wall. And the strength provided by three-side bounded brick wall, because there's one opening at the left-hand side or the right-hand side, so that the strength is less. Since there are different kinds of vertical members, with different dimension, maybe with different clear heights, with different cross-sectional area. Therefore, all the vertical members may not develop their ultimate strength at the same time, so that the sum of lateral strength by the vertical member have to be reduced, and the reduction factor for the ultimate lateral strength, beta, is assigned to be 0.9. Therefore, VBS is the base shear strength of the building, equal to beta times VVM, and VVM is the sum of the lateral strength of all vertical members. And here's a procedure to find out the ultimate strength or the base shear strength of a building. Step 1, measure the cross-sectional area of the vertical members, including column, reinforced concrete walls, four-side bounded brick walls, and three-side bounded brick wall. Step 2, collect the lateral strength per unit cross-sectional area. That means that before arriving at the school building, we have to gather the information about the lateral strength per unit cross-sectional area, including column, reinforced concrete wall, four-side bounded brick wall, three-side bounded brick wall. And step 3, after measuring the cross-sectional area of the vertical member and gathering the information of unit lateral strength of the vertical member, so that we can compute the sum of lateral strength of all the vertical members. VVM equal to tau C times AC plus tau RCW times ARCW plus tau BW4 times ABW4 plus tau BW3 times ABW3. And then also we gather the information about the reduction factor for the sum of the lateral strength, beta equal to 0.9. So that finally we can compute the ultimate strength of the structure, VBS equal to beta times VVM. That's the seismic capacity of the building. And here is an example taken from the Rui-Pu Elementary School at Taoyuan County. And here's a building in the school. That's the front view of the front photo of the building. And here is the rear photo of the building. And we are going to compute the seismic capacity of the building, VBS equal to beta times VVM. And here's the elevation of the building, and here's the plan of the building. And they are totally, the cross-sectional area, the dimension of C1 equal to 35 cm by 40 cm. There are totally 14 columns of C1. 1, 2, 3, 4, 5, 6, 7. 7 times 2 equal to 14. And embedded in the brick, in the partition wall, there's a column of C2, and the dimension of C2 is 24 centimeters by 40 meters. There are totally 3 columns. 1, 2, 3. 3 columns of partition wall. And the total number of stories, NF equal to 2, first floor, second floor. Then we can calculate the unit lateral strength for column of classroom. Tau C1 equal to 1.8 NF equal to 2 plus 4 equal to 7.6 kgf per cm square. and the cross-sectional area of a column of classroom equal to AC1 equal to 35 times 40 equal to 1400 cm square, and the number of columns of classroom NC1 equal to 14, so that the total lateral strength contributed by the column of classroom VC1 equal to tau C1 times AC1 times NC1 equal to 148.96 ton-force. And then we move to the columns of partition. And from previous slide, we have the unit lateral strength for columns of partition equal to 2.6 kg per cm square. It has nothing to do with the number of stories. And the cross-sectional area of the column of partition equal to 24 times 40. 24 times 40 equal to 960 cm square. And the number of columns of partition NC2 equal to 3. So that the total lateral strength contributed by the columns of partition VC2 equal to tau C2 times AC2 times NC2 equal to 7.488 ton-force. Once we have VC1, 148.96 ton-force, and VC2 equal to 7.488 ton-force, so that we can compute the total lateral strength of the all vertical members, VVM, and VVM equal to VC1 plus VC2, because in this case, there's no reinforced concrete walls, there's no four-side bounded brick wall along the corridor, and no three-side bounded brick wall along the corridor. So that VVM equal to VC1 plus VC2 equal to 156 ton-force. Once we have the sum of the lateral strength of all vertical members, and is reduced by 0.9, so that we can have the ultimate base shear strength VBS of the building. VBS equal to beta times VVM equal to 0.9 times 156.448 equal to 140.8 ton-force. That's the seismic capacity of the building. And how do we have the unit lateral strength of those vertical members? Here we take column as an example. And this is the column line taken from the two-story building. And there will be 4 failure modes. The first one is shear failure of the column on the first floor. And the second one is the flexural failure of the first floor column. And the third one is the flexural failure of the beam in the second floor. And the fourth one is the flexural failure of the beams on the second and roof, and on the second floor and the roof. From the first failure mode, then we take the free body diagram here. This is V1, that's the lateral strength of the column line under shear failure of the first column floor, of the first floor column. And from force equilibrium, we know that V1 equal to Vn. Vn is the shear strength of the column. And here's the second failure mode. That's the flexural failure of the column on the first floor. And from this failure mode, we can have the free body diagram here. MC1 is the first floor column flexural strength, and V2 is the base shear strength of this column line. And from the moment equilibrium, then we can have V2 equal to 2 times MC1 divided by H. MC1 is the first floor column flexural strength, and H is the clear height of the first floor column. And we move to the third failure mode. And from this failure mode, we can draw the free body diagram. And MB2L is the flexural strength of the column on the second floor of the beam. That's the left-hand side. and the right-hand side is MB2R. B stands for beam, 2 stands for the second floor, and R stands for the right at the right-hand side, and M is the moment strength of the flexural strength, and MC1 is the flexural strength of the column on the first floor, and MC2 is the flexural strength of the column on the second floor. And alpha 2 and alpha 3 is the coefficient according to the vertical distribution of the seismic force, and V3 here is the seismic force. From the reinforcement, we can have the information MC1, MC2, MB2L, and MB2R. And then from the weight and elevation of the floors, we can have the coefficient for the vertical distribution of the seismic force, alpha 2 and alpha 3. Therefore, in this free body diagram, only V3 is unknown. And from moment equilibrium, we can solve for V3. And this is the fourth mode. Here is the beam flexural strength at the left-hand side, and here is the beam flexural strength on the right-hand side, and here is the beam flexural strength at the roof on the left-hand side, and here is the flexural strength of the beam of the roof on the right-hand side. And alpha 2, alpha 3 here can be obtained from the vertical distribution of the seismic force. Therefore, in this free body diagram, only V4 is unknown. Therefore, according to moment equilibrium, we can solve for V4. Once we have V1, V2, V3, and V4 from 4 failure modes, we can have take the minimum one. The minimum one is the lateral strength of the column J. Once we have the lateral strength of column J, then we divide the cross-sectional area of the column J, then we can have the unit lateral strength of column J. That's the lateral strength per unit cross-sectional area. Then we repeat this process for different columns, so that we can have the average one. That means the summation of from J equal to 1 to NC. NC is the number of columns, tau Cj, and then divided by NC, then we can have tau C, the average unit lateral strength of column. That's the lateral strength per unit floor per unit cross-sectional area of the column. And here's the reference for this lecture. The first one is the Seismic Design Code of Buildings, published in 2011 by the Ministry of Interior. And it can be downloaded from this link. And the second one is Structural Concrete Design Design Code, published in 2011 and also by the Ministry of Interior. And you can download this without any charge from this link. And here's some videos. The preliminary evaluation one, the English one is the current one. It will be uploaded later. And this is the Chinese version. And 1-2, the seismic upgrading of school building, the English version. And 1.1 is the strategy. 1-1 is the strategy for earthquake disaster prevention. This is the English version. This is the Chinese version. And in this lecture, we focus on seismic capacity of a building by preliminary evaluation. In order to calculate the seismic capacity, we have to know about the cross-sectional area of the first floor vertical members. That means that a professional engineer have to arrive at the school building and measure the cross-sectional area of first vertical members, including reinforced concrete column, reinforced concrete walls, 4-side bounded brick wall, and 3-side bounded brick wall. And the professional engineer have the unit lateral strength of the first floor vertical members in advance. And from this information, tau and A, the engineer can calculate the sum of lateral strength of the first floor vertical member, VVM, because not all the vertical members develop its strength or their strength at the same time, so that there's a reduction factor for the lateral strength beta. From beta and VVM, then we can have the base shear strength of the structure, VBS equal to beta times VVM. That's the seismic capacity of the building. And this video will be uploaded into this channel here. That's all for this lecture. Thank you. See you next time. Bye-bye.